Hello, everyone. In this video, we are going to be talking about how heat, mass, and momentum all relate from the perspective of their individual fluxes, looking at how each of their respective concentration gradients all use a diffusivity that has a unit of meters squared a second. So before I begin with the mathematical demonstration, something I'm going to do is define what diffusivity is so that we can understand what we're talking about when we're trying to find this. So, diffusivity. So if we look at the units of diffusivity, meters squared a second, it's immediately kind of clear what we're observing. We're observing how something spreads across an object over a period of time. Let me go ahead and write that. Something spreads object over a period of time. So let's go ahead. This kind of makes more sense when you look at the individual equations of flux, because then you can actually see how it relates to a corresponding gradient. So for our first example, I'm going to go ahead and observe heat flux. The equation looks a little something like this. Heat flux in regards to pressure and the, let's see here, specific heat. And then we have, let's see here, diffusivity constant, which is negative because remember, anything involving heat, anything hot is always going to flow into something cold. So we make it negative to correspond with that. And then we're going to have our temperature gradient, which is from our change of temperature over a change of distance. This can be X, Y, or Z. I just use X because that's what I'm more familiar with. But to prove that this diffusivity constant is in meters squared a second, we're going to go ahead and combine all units from the heat flux and the temperature gradient, and then simplify it to the meter squared a second. So if we look at heat flux, the units look something like this. Now we're going to take the inverse of the pressure, which is brain fart here, meters cubed over kilograms. We're going to multiply this by the inverse of the specific heat, which is kilograms Kelvin per joule. And then we're going to multiply this, or we're going to divide this by the temperature gradient, which would be change of temperature, which is Kelvin, over change of distance, which is meters. So if we cancel out some units here, we have meters to the power of 4 over seconds times meters squared, or meters squared a second, which I'm actually going to move this over here just for the sake of space. So there we go. That is how we prove it with heat. So let's go ahead and move on to mass. So mass is a different looking equation. We have our mass flux, G and dA, and we set this equal to the negative diffusivity of mass. And we're going to instead look at, instead this concentrate, this gradient is going to be concerning the concentration of the mass. So we're going to do concentration gradient over a change of distance, which again, we're just going to keep d of x. So how do we prove that this guy is meters squared a second? If we look at the units for this, let's start with our right side here. Left side gets kind of fuzzy for me sometimes. So the gradient, remember a gradient is simply uh meters cubed per a, or your volume over a weight. So we're just going to make this meters cubed over kilograms. And then we're going to multiply this by the change of mass, which in this case is meters. And then we're going to go ahead and relate this to our constant over here, which should be kilograms meters squared a second. Or I should say, sorry, the gradient is kilograms over volume, and then we switch it around because we're obviously dividing by it. My bad. So if we look at this, kilograms cancel out. We're left with meters 4 over meters squared a second, which simplifies to meters squared second. And we have got our diffusivity units, just like that. Now, lastly, we're going to demonstrate this with momentum. So we're going to look at the momentum flux, which uh, the flux of momentum is shear force over pressure, which is set equal to mu pressure times the the velocity of a fluid's gradient, which d of u is the velocity of fluid. All right, so we're going to do the same thing. I'm actually going to turn this into negative mu just for the sake of simplifying this. This is negative mu is how this would also be expressed as. So shear stress, well, that is kilograms meters squared a second, and we're going to multiply it by the inverse of pressure, which is meters cubed per kilogram. And then we are going to go ahead. Uh, we're going to do the inverse of velocity, which for meters per second, we would go from seconds per meter, and then divide or multiply by our mass to cancel that out, which gives us m. So we're going to cancel these out. Right. Oh, did I do something wrong? I feel like I did something wrong. This isn't supposed to look like this. Oh, I see what I did wrong. I see what I did wrong. This is actually in kilograms meters second squared is what that's supposed to look like. And then we do meters cubed per kilogram. So sorry about that. And then we multiply it by m, and that gives us our units. So sorry about that. We're going to simplify our kilograms, simplify our seconds, and we are left with meters squared second with the diffusivity. So I'm going to go ahead and just kind of like, because I know that's kind of confusing to follow. But yes, as you can see, we have related heat flux, momentum flux, and mass flux with a diffusivity in regards to a concentration gradient and proved mathematically, once all units are simplified, that the diffusivity is always going to be in meters squared a second. In this part of the video, I will explain Fourier's law, what the units of heat flux, diffusivity, and temperature gradient are, and why there is a negative sign on the diffusivity. I will also explain in this video the difference between conductivity and diffusivity and how they're also related to each other. So let's start with what Fourier's law is. Fourier's law is the phenomena in which we observe the hot regions of an object transferring heat to the cold regions of an object, and how this heat flow is proportional to how quickly temperatures change with distance. So let's go ahead and express this with an equation. So I'm gonna write down Fourier's law. Just gonna make sure that this is recording. Okay, cool. Right, Fourier's law. Okay, so the equation of this is our heat flux. set equal to our thermal diffusivity, which we say is a negative alpha. And then we're going to put this over, and we're going to multiply this by our temperature gradient, d of t over d of x. To explain, that is our change of temperature in a change of distance, which I have just set to x in this case. So let's go ahead and start by breaking down the units of this equation. So our heat flux is going to be in regards to joules per meter squared second. Our diffusivity, which we talked about in the first part of the video, is always going to be in meters a second, or meters squared per second. We're going to multiply this by our temperature gradient, which is going to be in Kelvin per distance. Just to kind of quickly explain what each of these units are and what they're doing. For heat flux, obviously we can tell that this is heat or not heat, this is energy in regards to a surface area of time. So how much energy is moving through a certain is moving through a distance. And then we have our diffusivity, which we explained is just how quickly something is moving across an object. And we have our temperature gradient, which is a change of temperature over a change of distance. Pretty easy to interpret. So let's go ahead and start by explaining why is this diffusivity negative in this case? A way to show this is by showing the graphical relationship between temperature and distance for an object. So I'm going to quickly make a little graph over here to show you what I mean. So we're going to put this in temperature, which I'm just going to put in degrees Celsius, and I am going to put this in distance in regards to meters, or x, what we were talking about earlier. So let's say I have initially an object at 400 degrees Celsius. Put way over here to the right side of an object. Let's say we have the left side and we want to know what the heat flow is going to look like going to the left of the object. Oh, did not mean to do that. Very sorry about that. Right side. And we are concerned not with the left, we are concerned about the heat flow. So as I explained, this is Fourier's law studies how hot regions of an object transfer heat to cold regions of an object. So we have a heat source coming from our right side, and our left side, we're just going to put this in a vacuum, or we're just going to say there's nothing on our left side. So as you can imagine, our temperature is going to steadily go down as it transfers through our object. Well, why is this? Well, imagine this. When you put something warm on the right side of a block, that right side of the block is going to be close to, if not the same temperature of the source of heat. But as it travels through an object, the heat capacity of the object will begin to steadily absorb energy as it passes through. And once it eventually gets through the left side, you're going to come out not at the same temperature as the source, but often much lower. So let's call this arbitrarily like 200 degrees Celsius, something like that. And we observe that this temperature gradient, or this change of temperature in regards to the distance, is actually a negative relationship. Thus, why we put the negative sign on this thermal diffusivity. Okay, well, that explains that, but let's go ahead and look at another part of this. Let's explain the difference between this diffusivity and the conductivity of an object. So, conductivity versus diffusivity. Okay, so what is conductivity? Conductivity, easily explained, is how easily an object can store energy. Let me write this down. So, in units of, usually we express conductivity with K. How easily an object can store energy. Think of it like this. Compare like an insulator to a block of metal. A block of metal, when you heat it up, is going to absorb and store the energy much easier. If you have a heat source on one side, you can touch any part of that metal and it is probably distributed and stored that heat much better and it will stay warm for a while. That is because it has a high conductivity. Let's compare this to the insulator for a coffee cup. When you have an insulator in between a piping hot cup, that insulator will actually ensure that you don't end up burning your hand because it is terrible at storing energy and it does not contain any heat for us. So we're able to easily pick up the cup. That's what high versus low conductivity looks like. This is different to diffusivity. Diffusivity, which we call alpha. I think the best way to describe this versus conductivity is showing how they actually relate to each other. If you look, diffusivity actually equals conductivity over density and heat capacity. When you look at this equation, you can actually kind of immediately tell what diffusivity is about. Diffusivity concerns the conductivity of an object in regards to its density and heat capacity. Because think about it, as heat is passing through an object, the speed in which that can spread obviously varies depending on how dense a material is. If you have a more dense object, chances are it's going to take longer for that heat to transfer or its heat capacity. If its heat capacity is high, you can imagine as the energy stores through, it's going to make it so it takes longer for that energy to come through because the individual molecules can now store more heat in its system, thus making it take longer for it to spread. So, diffusivity actually uses conductivity in its calculation to determine how long it will take for an object to heat up or how quickly the heat will take to travel through a system. And that is this part of the video explained. Thank you very much.